All right, so these dienes can undergo a very interesting reaction called the diels-alder cycloaddition. And so in this case, we have a reaction between our diene and another alkene that's known as a dienophile, right? So that means diene loving. And so we combine these two components to form a cyclohexene, right? So a cyclohexane with one double bond. And so if we take a look at the mechanism of this reaction, it all occurs in one step. And so this is what's known as a concerted reaction. And so the way we draw this is that either one of these pi bonds, it doesn't matter which one of them will attack the dienophile. The dienophile will then attack the diene. And then this one of these double bonds will form the double bond in our cyclohexene. Right, so it ends up looking something like that, where this bond, this pi bond, now becomes this sigma bond. This pi bond becomes this sigma bond, and this pi bond stays a pi bond but moves on over, right? So keep track of where all these things are going. And so this is different than the ionic or the radical reactions that we learned. This is what's known as a pericyclic reaction. And this is the only pericyclic reaction we'll learn in this course, but as you move on through chemistry, you'll learn other pericyclic reactions. And so just some properties of some pericyclic reactions is that they're concerted. And so what this means that this all happens in one step. So there's no intermediate. And so although we're drawing these arrows, it might look like it's happening stepwise. It all happens in one step. And then it's cyclic, of course. So the transition state is cyclic. And so this is a very powerful reaction. The Diels and Alder, the guys that discovered this, won a Nobel Prize for it. And there's some very cool things about this. First off, it's another carbon-carbon bond formation reaction. So in this course, I think this is only our second carbon-carbon bond formation. And this one doesn't require extreme conditions. Right, we're not using a very strong base at all. And then the other cool thing is that it gives us access to cyclohexanes or cyclohexenes in this case, but we could further reduce it, very easily. And these are very common in nature due to cyclohexane being very stable. And so being able to synthesize it in kind of one step with high yield is very good. And then finally, the last thing that we'll learn later on is that we have a lot of degree of control over this when it comes into terms of the stereo and regio chemistry. This is a reversible reaction. And so if you have cyclohexene and you put it in high temperature, it will reverse to form your diene and dienophile. If you think about why this requires high temperature, think about it. You're going from one molecule to two molecules. So this reaction has a positive entropy, positive delta S. And so that's favored at high temperatures. If you think about delta G equals delta H minus T delta S.